Hey guys, alrighty, we're going to talk about structural members and some properties of them. This is materials that are used to build structures. Okay, so first concept that I want you guys to have down is moment of inertia, a mathematical property that gives a cross-section, and so that is measured in inches to the fourth power, inches quadded, maybe, that gives an important information about how the cross-sectional area is distributed about the center. Centroidal axis means the very center of that shape. Okay. It is related to the stiffness of the object, how much basically the beam is going to deflect is what we're focusing on here. So thinking about these two diving boards, the one on the left, you'll notice that it has a lot of overhang, and so it's probably going to deflect a lot more than the one on the right. There's not very much overhang there. So a diver standing on one of those short diving boards, there's not going to be as much deflection. Okay, that's what we're really looking at today. So in general, a higher moment of inertia produces a greater resistance to deformation. So the higher the number that you get when you calculate moment of inertia, the less it's going to deform. So that said, which of these two diving boards, the one on the left that's like a traditional diving board that you'd find at your pool, or the one on the right that's like for a competition, divers diving off at a competition, which of those would have a higher moment of inertia? Okay, so you're going to be taking in a lab today a piece of wood, a 2x6, and you're going to try standing on it in two formations. The first way that you're going to try is in plank formation, shown here as option B, and then the other way is joist, option A here. And you'll see that joist is when you have it upright, and plank is when you have it flat. And so the idea here is that if we think about beam A and beam B, which of those is going to have a greater resistance to bending and therefore a higher moment of inertia? What do you guys think? Good. Hopefully you said that beam B would be deflecting more than beam A. And just how much more is what we're going to be doing in our experiment today. Okay, so why did beam B have a greater deformation than beam A? That has to do with moment of inertia. It has to do with how much of the material is distributed vertically as opposed to horizontally. Okay, so how the material is distributed about the orientation of the beam, due to the orientation of the beam. All right, we're going to do this simply with rectangles. You get very more challenging beams when you get into real civil engineering. You get hollowed out pieces, you get C-channels, I-beams, and things that are going to be a little bit more challenging. But to keep things nice and simple for us as we introduce the concept, we're just dealing with rectangles. So you just have to worry about base and height. Okay, now here is the calculation, which I know looks a little bit of a mess, but it's really not too bad. So I, with the two little x's next to it, that stands for moment of inertia. And that's calculated by base times height cubed. And the only thing that's being cubed there is the h, just height. Base is not cubed, just height, divided by 12. You're measuring the base in inches and the height in inches, and that's where that dividing by 12 is going to come into play. Okay, so here's an example. We have a plank that is 5.5 inches by 1.5 inches, which is basically a 2x6 that has been milled down. Okay, and so what you're going to do is 1.5 inches times 5.5 inches cubed divided by 12. And yay. Okay, that gives us about 21 inches to the fourth power. Because notice you're taking inches times inches cubed, so that gets us inches to the fourth power. All right, now if we take that exact same beam, we turn it flat. Notice that this time we'll do 5.5 inches times 1.5 inches is the one that's being cubed. So when it's flat, the shorter dimension is the one that's being cubed, so it's not going to make this answer as big, and we only get 1.5 inches raised to the fourth power. A huge difference. Okay, so you can see why there's such a dramatic difference in how much these two beams deflect. Now, granted, this is a bit, well, I mean, depending on how long that beam would be, it's not that exaggerated, actually. It's a bit exaggerated, but not too much, and you guys will see when you start to stand on those beams. When you have a shorter beam, of course, you're not going to get as much deflection. The longer the beam is, the more deflection that you'll get, and that is actually another characteristic that's going to be important here. Okay, so yeah, beam A, when we have it joist, that is actually 14 times stiffer than when we have it plank. Okay, this is one of those slides that PLTW puts in here and then they don't tell you why. Why are composite shapes used in structural design? I don't know the answer to this, but those are some composite shapes. I don't know. You tell me. Mr. Scharnhorst is there. Maybe he knows. Ask him. Okay. Non-composite versus composite beams. Doing more with less. Okay. Oh, well, I guess they're trying to say, I guess you can see that you can get a much higher moment of inertia, but still have a really small cross-sectional area. So we've got in the middle a moment of inertia of 130, but we only have to use 10 inches squared as opposed to the one on the right that's 178 inches to the fourth, that moment inertia, and a much higher area to get that as well, so making that I-beam. I guess that's what they're meaning. Okay, woo. Okay, structural member properties. Okay, chemical makeup. So this is getting into the modulus of elasticity, the stiffness of the actual type of material that you're using. That's the next important part. So like, are you using wood? Are you using some kind of a fiberglass material, metal, etc.? How much is it going to allow itself to deform? That's another characteristic that's important here. So higher modulus of elasticity means greater resistance to deformation. So just like a higher moment of inertia meant greater resistance to deformation, so does higher modulus of elasticity. Basically, a higher modulus of elasticity actually means it's like less springy, it's less elastic in a way, is kind of how I've come to think of it. Okay, so this is showing you two different beams. Beam A is Douglas fir, which is wood, and beam B is a type of plastic called ABS, and just showing you the different properties that could have. So what distinguishes between these two beams? They're going to have a different chemical makeup, and that can result in a different amount of deformation. So a different modulus of elasticity in this case. Okay, and so you can see the Douglas fir actually will have a greater stiffness, greater resistance to deformation, which means that it has a greater modulus of elasticity than the ABS plastic, which is in the back. Okay, so why did beam B have a greater deformation? It's the modulus of elasticity. So it's the ability of the material to deform and then return to its original shape. Okay. And then those are the characteristics that affect an object's deflection. And deflection is going to be given by this delta symbol. The triangle means delta, which is change. Delta max means the maximum that the beam actually shifts from its original position. So how far is it actually moving from its original position? Okay. So we apply a force or a load to the beam. The length of the span between supports, longer the span between the supports, the more we're going to see a deflection. Modulus of elasticity, higher modulus of elasticity means less deformation. Higher moment of inertia also means less deformation. Okay, and then so here's just a little bit more information about those materials. The modulus of elasticity, you can see for the Douglas fir, it's a very, very high number, 1,800,000 psi, which stands for pounds per square inch. And then the modulus of elasticity for ABS plastic is much, much smaller, about a quarter the size, only 419,000 psi. Everything else about the beams is exactly the same as the modulus of elasticity. That is very different there. And those modulus of elasticity being in those hundreds of thousands or millions of psi is very common. So when you're calculating modulus of elasticity, you should be expecting numbers of that magnitude. Okay. So now you can calculate beam deflection using those pieces of information. Force, length, that means the length between the supports. So not including the supports, but between the supports. And then E stands for modulus of elasticity, that really, really, really big number. And I stands for moment of inertia. So given the information down below, we can actually calculate how much this beam, piece of Douglas fir, with a load of 250 foot-pounds. What the foot-pounds means is that's just like an English measurement of weight. And yeah, so we can just plug in those numbers. So for the force F, you're plugging in 250 pounds. For the length, that is 96 inches. We do want that to be in inches, so 8 feet times 12 gives us 96 inches. Remember to cube just the length there, not the whole thing up there, just the length. Then underneath, we've got 48, and then the modulus of elasticity, and then the moment of inertia, 20.8 inches to the fourth. And we get a maximum deflection of 0.12 inches, so less than a quarter inch. Very, very small. All right, so we really, especially in joist, you really won't see much of a deflection. It's going to be very, very tiny, but should at least still be measurable. When you are in the plank orientation, you should see more of a deflection. Okay, and then let's go ahead and calculate the beam deflection for this beam here. For the ABS plastic, the only difference in this case is that the modulus of elasticity is much, much smaller, 419,000 psi. Everything else is the same. Plugging those numbers in, we should get 0.53 inches, so over half an inch of deflection, even in the joist position. Okay, so you can then compare the ABS plastic to the Douglas fir and see that we should get a much higher deflection with the ABS plastic. That is definitely a dramatic excuse me, a dramatic GIF, really exaggerated, but you get the idea. Okay, all done. I hope that wasn't too long, and good luck on your lab, everybody. Thank you.